This is picking up from where I left off in the first video for these decision-making processes. So I was about to tell you that I was going to put in the normal CDF and 2.67 to 8.44. And when I do that, I get 0.00 and 3/8 will be my probability here. So this is the normal approximation for this binomial probability. And because we do have a TI calculator, obviously. If we did not, by the way, you would be simply finding this for um, on your z-table, and with your z-table, this probability of being 2.67 up to 8, that's basically into infinity, right? So you could essentially say that this is on out. So all you're doing is finding the same as being greater than 2.67 or being less than 2.67. I think I have my tables up here. Let me see. It's not this one, obviously. Here's the t-table I've been using. Let's go back to the z. So being greater than 2.67 is the same as being less than 2.67, so negative 2.67. So if I go across here to negative 2.67, you see that exact same probability right there. Now, if we do indeed have a calculator, which we obviously did because I used it, we could actually find the exact probability of this binomially distributed random variable. But it would be a multi-stepped process as well, which makes it even more work, even with our calculator, because we'd have to find the probability of being less than 119, and then we'd have to subtract from that the probability of being less than 78. So even with our calculator, this would be a little bit more difficult probability, and the normal approximation might be the preference on that. Okay, now I'm going to go ahead and go on to problem number 3. So in problem number 3, let's read it. A random sample of 12 babies showed that an average age in weeks at which the baby started to crawl to be 38.3 with a standard deviation of 10 weeks. Using this information, construct a 95% confidence interval for the true average age in weeks at which all babies start to crawl. So first of all, this one's pretty obvious. It says confidence interval right here. And then it says for which all babies start to crawl. All assumes the population, right? That's all babies out there. That's the population of babies. So what we have going on here is a sample of size 12. We have a mean of that sample to be our x bar, and that x bar is 38.2, and those are weeks, and we have a standard deviation of 10 weeks. So these are our sample pieces of information. And if we're going to have a confidence interval, we're going to need to know that these things are approximately normally distributed. Weeks in which the baby crawls is approximately normally distributed. That should really be told up front. So we're just going to make that assumption that we have that because we haven't been told, and we're going to assume that the teacher doesn't not want us to do anything. Anyway, so 95% confidence interval here. And if our n is less than 30, we are going to use a t-distribution. So in order to do a 95% confidence interval, we have to have those critical values, right? So we're going to get our critical values based upon the 95% right here in the middle, and that is going to give us our appropriate t-values. Now our t-values will have 11 degrees of freedom, and that's going to give us our t's. And the negative one goes over here and the positive one goes over here. I'm only going to write it one time, obviously, but those would be the cases. So I have to go pull up the Bioga t-tables because I haven't had those and I want to start using them this go around. Okay, so here's our T table from Bioga. So we're going to look up the 95% confidence. We have 11 degrees of freedom, so we're going to move down here to our 11 degrees of freedom. So, oops. So 11 degrees of freedom right there with 95% confidence. So this is the 2.201. So that will be our T. So we're only going to use 2.2 here. So 2.20 is all we're going to use because that's what Bioga is typically using. I'm going to go ahead and change back over here now that we have that value. So now what we have to do is we have to calculate our confidence interval. So confidence interval starts with the point estimate. That's our sample mean, 38.2 weeks, and then says plus or minus the margin of error. Plus or minus, the minus and the plus come from this t-value. We have to start out with our critical value. This, remember, is called a critical value. A CV is what I call that, critical value. And then 2.0 is the critical value, and then that gets multiplied by the standard deviation, 10.0, divided by the square root of the sample size, which is 12. So the way I'm going to calculate this is I'm going to calculate this margin of error first, so 38.2, and then plus or minus, and my calculation is going to go 2.2 times 10, and then divided by the square root of 12. And so what I get here is 6 point, and I'm going to go 35, just to keep one more decimal, just so I make myself feel good about this. And then I'm going to go over here and I'm going to calculate the interval. I'm going to do 38.2 plus this to be my right side, 38.2 minus this to be my left side. So 38.2 plus 6.35. And that's going to give me 44.55. And then I will do the minus entry, and that gives me 31.85. And now I'm going to give this as an interval with the mean in the middle, and I'm going to round it appropriate one more decimal than the original, right? So 31.85, and if we needed to round it to the exact values that it was given here, then we would be rounding it to 31.9, and then over here for 44.5, that's one more decimal than the original was given, but again, if we were going to round it to one decimal, and Bioga is usually very good about telling you where a round off is there, so pay close attention, then we're going to round it to 44.5 weeks. Now, the interpretation of this is with 95% confidence, we feel that the true population average number of weeks at which a baby starts to crawl is 31.85 to 44.55 weeks. All right, now we're on to problem number 4. So next on problem number 4, we read the problem. The following data represents the number of days of incubation for 21 randomly selected Rhode Island red hens. Compute the following for this data. Assume the days of incubation is a normally distributed random variable with mean and standard deviation calculated from the data. What is the probability of choosing a random Rhode Island hen that has been incubating longer than 512 days? Okay, now the first thing that we're going to have to do is we're going to have to input this into our statistics register. And then we're going to have to do summary statistics on that so we can get our mean and our standard deviation so we can begin answering this question. And we are going to answer this question just based upon this sample data. It really should be population data, but a lot of times you'll answer questions based upon sample information. This is asking us for a probability, right? What is the probability? And it says that incubation, so our random variable is representing the number of days to incubation, okay, that's our x. So x, number of days to incubation, is longer than, so that's a strict inequality, greater than, and it's 512 days. So I'm going to need to input into my calculator so that I know all of my sample statistics here. And it really is an X bar, but I'm going to call this X bar instead a mu. And then it's really an S, but I'm going to call this S a sigma, just so that you don't get too confused. So we have 21 randomly sampled hens, and I'm going to use my one variable stats to calculate this mean and this standard deviation based upon all of these 21 data points. Okay, so these are the summary statistics. Now remember, this is a sample. So X bar was equal to 490.66666, and so I'm rounding it to one more decimal than the original data. My standard deviation, remember, is actually S sub X. Remember, you don't want the value that is the population one. This is not a population. You don't use this one, okay, sigma sub x. It's the S sub x, but we're just calling it for namesake sigma here so that we don't get confused of what we're actually doing. So I got those from one variable statistics, and then my sample size was 21. So now what I need to do to find this probability is I need to standardize. So I'm going to standardize the x, right? I'm going to take the 512, which is my random variable x, and I'm going to subtract the mean from that, 490.7, and then I'm going to divide it by my standard deviation, 29.9. Now the only other thing that I need to be careful of is I'm asking, is it about x's or is it about x bars? And so I need to question that. So if I go back over here to the questions and I say, what is the probability of choosing a random Rhode Island hen? So if it's a random, right, a single one, then it's not this. So this is not the case. So this is simply just dividing by 29.9. So now once I've done that, now my probability is going to be the probability of a z being greater than, and I have to calculate that value, 512 minus 490.7, and then divide that by 29.9, and I get 0.7123. And remember, it's a z-score. I need it 2 decimals, so 7.1 is fine. And now, in order to get this probability, I'm going to do one of two things, right? I'm finding this probability here. Here's my little curve. I'm finding from a 0 here that being greater than 0.71, I'm trying to find this area under the curve. So I can do normal CDF, and I can start at 0.71, and then I'm going to infinity, which we're going to use a 9 for that, or I can go look it up in a table. So I'm going to do second function variables, normal CDF. I'm going to input my left boundary as 0.71, and then my right boundary is a 9, and I'm going to get out 0.2389 when rounded. 2389. 2389 when rounded. And so that will be my probability. Now remember that I can also go to my z table, and remember that the probability of being greater this is the same as being less than a -1, so I can look down here at a negative 0.71, so here's my -7.1, and see there's the exact same probability that I calculated for there as well. Now I'm going to stop here, and the next time we'll pick up in the video 3. So we'll do 5 at that point.